Okay, here's a set of 4 problems that are related that I did not do in the original video. So here's the diagram. There are 2 larger masses on a fixed bar, fixed in place. And then there's this strip or thread or wire or ribbon hanging down connected to the center of this very thin bar and 2 smaller masses. And so as the small mass attracts to this mass and this small mass attracts to this mass, there's going to be a force in this direction, which is a counterclockwise torque, and there'll be a gravitational force on this mass in this direction, which is a counterclockwise torque. And so as this twists, the position of the laser beam off the mirror on the ruler is going to shift, and as it shifts you can measure how far it goes, and we can use that to get the constant g. Remember, constant g is 6.67 times 10 to the minus 11, pretty small. So you're going to have to expect that the gravitational force between these masses is going to be pretty small. So this is a diagram, but here's a picture of an actual apparatus that we could buy. I was thinking about buying one, but it's $2,500. So you see the 2 large masses, and inside this case the small masses hanging from a strip, and there's a little mirror there. And the reason this is inside the case is the tiniest disturbances in the air or vibrations, anything will knock this off. The forces are so minuscule. But this is an actual apparatus that we could buy from a scientific supply company for $2,500 and actually measure that very, very tiny value for G. So number 11 is pretty straightforward. You're just calculating the force between these 2 masses. So you put in the mass of each and make sure they're both in kilograms. And the radius has to be in meters. And the reason is that G, and you should be writing units, G is 6.674, if we add another digit, newtons meters squared per kilogram squared. So for the kilograms to cancel, the 2 masses must be in kilograms, and for the meters squared to cancel, giving you a force in newtons, the R has to be in meters. And don't forget to square it. So those are a few mistakes you can make, but it's pretty straightforward. And of course I left out the times 10 to the minus 11. So you can imagine that the masses aren't that big, and the R is small enough that it will make it larger, but it's still going to be a tiny, tiny, tiny force. Remember, a force of 1 Newton is only equal to the weight of about a quarter pound. It's not a big force in itself, and so if you get something like 10 to the minus 8, you know that that's an extremely tiny force, and that's why you have to worry about air currents, or almost anything could overpower that force. So here's a top view of the apparatus, which would be helpful. And remember, torque is RF sine theta. And so this has a force in this direction. The mass that's going to move. Remember, the red mass isn't going to move. It's only the blue mass that's going to move. And so the torque is the R. So it's from here to here. It's that distance. That's your R. Your F is the number that you just calculated in number 11, and you'll know whether it's correct or not. But here's where people go wrong. They think the theta is 90 degrees, and you can see it's not 90 degrees. So the way to get theta is to draw a triangle from the axis to the two masses at their center, and remember it's always center to center because the distance from surface to surface is going to be quite different than center to center. So from center to center, and then another line here, and that's an isosceles triangle, and this is the angle we want. That's the theta we want, this angle. Isosceles triangle, two equal sides, and this distance. And you can see it's a big angle, but it's not 90 degrees. So think about how to get that. Do you know? Well, if you don't, you should. There's actually many ways you can get it, but the easiest way, I think, is to bisect this triangle into two right triangles. And we know this distance. And we know this distance, and so the bisector is going to be half that distance, and with those two distances, you can get that angle. And that's the angle, that theta is the theta you need, right? It's the angle between the r vector and the f vector. It's important to be careful about that. And that will give you the torque on this one, but there's a torque over here, so you have to double that, because the torque over here is going to be the same r, the same f, and the same angle theta. So the total torque will be double those two torques, because in this case they're both torquing the movable bar, right? The red masses are fixed in a clockwise direction. So the problems lead one into the other. 11 gives you the force. That allows you to calculate the torque. Number 12 and number 13, you want to get, this is now going to move, and it's going to accelerate. And so you know that the sum of the torques equals the rotational inertia times the acceleration. And so the acceleration then is simply going to be the net torque, which we just found. And we just need to divide it by the rotational inertia. Rotational inertia of what? The rotational inertia of this object that's doing the twisting, the moving. And since the bar, that would be three objects. That would be a point mass, and a bar. But since the bar is listed as negligible mass, the rotational inertia of the thing is just going to be the inertia of the two balls. And since they're the same, we can just take, they have the same mass and the same r. What is r? I bet you can't answer it. What's r? Pause the video. What's r? R is the distance from the axis to the point. So that's the r, and it's the same for both of them. And so that gives you the rotational inertia, and that should give you the acceleration. And once you have the acceleration, the last part is a kinematics, rotational kinematics problem. As always, you should do these by yourself before you look at my answers. It'll work much, you'll learn much better. But anyway, 14, this is the one I would use. And why would I use that one? Because it starts from rest, so this is 0. And the delta theta, you say, but that's 2 centimeters isn't an angle, right? But we know how to get the angle. I hope you remember, it's the arc length over the radius, so we know the radius. And the arc length would be the 2 centimeters that it moves. So this would be 2 centimeters divided by the radius. As long as you put the radius in centimeters, or you could do them both in meters. But either way, you're going to get the angle, and we know this. And so doing the algebra, you simply get that the time is going to be 2 times the change in angular displacement divided by the angular acceleration, square root, and you know that's correct if you got the last problem correct. Notice, however, if you like, you could do this doing linear kinematics. Just use the same equation in the linear world, that delta x, right, equals Vx initial t, that's going to be 0, plus 1/2. And what's the acceleration here? The tangential acceleration times t squared. And so in this case, the time would be the square root of 2 times delta x. In this case, you can just use the 2 centimeters, but you need to change the angular acceleration to tangential, but you know how to do that. Tangential acceleration is simply the radius times the angular acceleration. That's right on your equation sheet. Remember, it's always the radius that converts the linear to the angular quantity. So that's another way, and it will in fact give you the same answer.